Have you ever watched an insect just walk on water and wondered how in the world it does that? Or, why honey pours so differently than water? Well, the answers are all around us in these two powerful, invisible forces. Today, we're going to unpack the science of surface tension and viscosity.
Now, these might seem like just kind of quirky questions, right? But they actually point to some really fascinating physics. And the forces behind these everyday things aren't just cool bits of trivia, they're actually fundamental to countless things we use every day. So let's start with the first one.
Okay, our first stop is surface tension. The best way to think about it is like a liquid's secret skin, a super thin, elastic layer that lets it pull off some pretty amazing tricks, like forming those perfect little water droplets. So what's actually making this happen? It really all comes down to a tiny game of molecular tug-of-war. See, inside a drop of water, every single molecule is being pulled on equally by its neighbors in all directions. But right at the surface, there's nothing pulling upwards from the air. This imbalance creates this powerful inward force, pulling all those surface molecules super tight, and that's what forms that invisible skin. And the cool thing is, you can see this force in action everywhere. It's the reason raindrops beat up on a leaf instead of just flattening out. It's how insects can skate across a pond without a care in the world. It's even why oil and vinegar refuse to mix in your salad dressing. It's this constant, powerful force shaping our world in all these small but really significant ways.
To really get what's happening, we need to zoom way in, down to the molecular level. Because surface tension is basically the result of this microscopic tug-of-war between two totally different kinds of forces.
So here's the key difference. You've got cohesion, which is the attraction between identical molecules, water sticking to other water. Then you've got adhesion, which is the attraction between different types, like water clinging to the side of a glass. Surface tension happens because right at the surface, that cohesive pull between the water molecules is way stronger than any adhesive pull from the air. And that super strong inward pull is what creates all the tension.
But here's where it gets really fascinating. We've actually learned how to hack this natural force. By understanding it, we can manipulate it for our own uses, something we literally do every single day when we wash our hands or do the dishes. And our secret weapon for this is something called a surfactant. You can think of these as special molecules designed to get right in between those tightly packed water molecules at the surface and just break up their strong bonds. By weakening that skin, they let water spread out and really get into grime, which, as you can imagine, is absolutely essential for cleaning anything effectively. And this right here gets to the heart of how surfactants are so magical when it comes to cleaning. There's this specific concentration, kind of like a tipping point, where these molecules just become incredibly efficient. It's known as the critical micelle concentration, or CMC, and that's the moment the real cleaning power gets unleashed. So how does this actually work? Well, when you add soap to water, the surfactant molecules rush to the surface first and get to work breaking the tension. But once that surface is totally full, and this is that critical micelle concentration we just mentioned, the extra molecules start to form these incredible little microscopic cages called micelles. These micelles are what trap oil and dirt, lifting them off whatever you're cleaning so they can just be washed away. Pretty clever, right? All right, let's shift gears now. We're going to move from the surface of liquids to what's happening on the inside. We're moving on to our second invisible force, viscosity. And this one is all about how much a liquid resists flowing. We all have a pretty intuitive feel for this, right? Honey, which flows super slowly, has high viscosity. Water, on the other hand, flows freely. It has low viscosity. At its core, viscosity is really just a measure of a fluid's internal friction. You could just call it thickness. So why should you care about this? Well, viscosity is absolutely critical in so many industries. Think about it. The feel of a face cream, the thickness of ketchup, the ability of engine oil to protect your car's engine at super high temperatures, it all comes down to getting the viscosity just right. And because it's so important, industries have created standardized grading systems, like this one for industrial lubricants. You can kind of think of it like shoe sizes. It creates a universal language, so an engineer can pick the exact thickness of oil they need for a specific machine to make sure it runs perfectly. And each grade you see here is precisely calibrated to be about 50% more viscous than the one before it. So we have these two really powerful forces, But, just understanding them isn't enough. In the real world, for products to work the way we want them to every single time, we have to be able to measure these properties with extreme accuracy.
I mean, for any company, getting this measurement wrong can be a total disaster. Imagine your favorite face cream being all watery, or the ketchup just refusing to come out of the bottle. That's exactly why being able to get repeatable, reliable, and accurate measurements is non-negotiable for product quality.
But yeah, getting it right isn't always a walk in the park. These are kind of the four big culprits that can completely ruin a measurement. Tiny air bubbles, a contaminated sample, a machine that's even a little bit off, or even just a small change in room temperature can throw your results way off. So at the end of the day, getting that precision all boils down to discipline and control. It takes really careful sample prep, making sure your instruments are calibrated all the time, and this is a big one, maintaining a super stable temperature, because even a tiny change can drastically alter a liquid's viscosity.
So there you have it, surface tension and viscosity, two invisible forces that are constantly governing how liquids behave all around us. It really makes you wonder, what other fundamental forces are out there, just quietly shaping our world every single day, hiding in plain sight? Thanks for joining us.